let's see if I can zoom in. Here, I would call that d phi. The differential angle of twist, right? And this segment right here, this portion right here, okay, that portion right there is like this length, okay? And if I look right here, this from here to here is also, it's the same dx, yeah? And what's even crazier is that, you know, like from my understanding of shear strain, this angle right here is the shear strain gamma. Yeah, it's that shear strain gamma. And this portion right here, let me use blue. This would be the radius, right? The rho, like this. And depending on where I'm looking at, I could look at it here and be rho, whatever, you know what I'm saying? It'd be rho. And so what I have here, do you remember like in calculus when they were doing, you know, like for small angle deformations, maybe in dynamics we did this. We had ds, rho, and d theta in calculus, and we said that for small arc lengths, we said ds is rho, d theta. Remember that? Yeah. So here, I could say that this segment, if I zoom back in here, this segment right here, if I call that ds, right? If I call that ds, that red is ds, and that ds is equal to rho times d phi, which is equal to gamma, the shear strain, which is just a length, an angle, gamma times dx. Did you buy that?
Yeah.
You buy that? All right, good. I buy it too.
Wait, on the paper, is this one rho or this one rho?
Rho would be from here to here.
Okay.
Yes, in the notes. Yes. And rho is really any distance to where I want the shear strain, right? So the way I've drawn it right here, I drew it to the outer surface, right? Here I drew it to the outer surface, which would be the max shear strain, right? But it's, you know, and then or the max strain. But I could do it to any intermediate distance rho, which would be some strain.
Yeah.
But this outer surface would be the max, right? It would be the max, okay? But it's all good. The relationship ends up being the same. And then here, this d phi would be gamma over rho times dx. Yeah. And then here, the challenge here is, let's see, I have gamma and rho here, and rho is any distance, right, from the center to the outer surface or wherever in between even. So by Hooke's law, from Hooke's law for shear stress and strain, Hooke's, I would tau is equal to g gamma right here. And if I substitute this, I would say gamma is tau over g. So I'm going to put that into this relationship. So here, d phi is equal to tau over g rho times dx right here. And then from the definition of shear stress due to torsion, I would say this tau is T rho over J. And so if I substitute that into there for tau, I would get T rho over G rho dx. And the rho's cancel. Bye-bye. Right there. And this says d phi equals T over GJ dx. Right. And so now, and all this is saying to me, I'm going to go over here. I'm going to go right here. So now if I have a length, an entire length of a segment, that means if I just integrate to get the entire angle twist for over that length, then all I have to do is integrate. And so here, phi, the angle twist, would be from whatever length I need, T dx over GJ. And depending on the rod, the internal torque can be varying, or depending on the loading, right? Or if I have like a tapered rod or something, my polar moment of inertia could be varying. And this would be this. So, but if I have a constant internal torque, and if I have J is constant, so in the case, I'll just rewrite this over here. In the case where, so here is this relationship phi, this angle of twist. And if I have a constant internal torque, okay, and a constant J, and assuming the same material, so G, then this thing just reduces to like the integral of dx. So that's why we could use like TL over GJ. And we're just summing the, and then we're going to have discontinuities and things just like we've done before, and we're going to sum those parts up to get the angle of twist. And that's it. That's the angle of twist in a nutshell. Hey. It's all good. All right, so we've been talking about power, and power again is work per unit time. It's got units of joules per second or Newton meter per second. It's also defined as a watt. The relationship between power and torsion is that power is equal to torque, the internal torsion, times the angular velocity. Angular velocity is just a measure of how fast something is spinning, right, or rotating, how fast something is rotating. And then the frequency is just another way. It's like a unit conversion from angular velocity to cycles per second. And one cycle is like going around in one circle, and that's the same as like one revolution, which would be 2 pi radians, and like a revolution. How long does it take for a new government? And so like here in this video, what we're doing is we're going to take this power and we want to relate it to mechanics of material. So there's like some interplay between dynamics and mechanics here, but we're not going to go too crazy into the angular velocity part. But we're going to say, okay, if I want to deliver a certain amount of power from an engine to, let's say, like wheels or cars or gears, right, how much torque is going to be transferred through that shaft, right? And that'll give me a sense of how much stress is associated, and then I can design. Okay. And so for us, the important relationship is if given a power requirement and an angular velocity or frequency, or like in a car, like an RPM, revolutions per minute, how do I determine the torque? So for us, we're going to be using this to get the torque T. This torque is P over omega. And what that means for a shaft, so like here if I have, let's say here, I'll just draw like an engine. This is an engine or a motor right here. It's connected right here, and then there's like gears that's attached to this, right? And this is a gear that's turning. And this might be turning like that because of the engine here, the motor or the engine. It's driving this shaft and turning this gear here. And basically what we're saying is that if I make a cut and I look at the inside right here, if I look at the inside, this, what is the internal torque that's happening due to the power requirement? Okay, and now we're going to be able to design based on that. Okay, so really that's it. And let's see. All right, so let's see here. What do we got? Okay, so that's just the, so we're going to design a shaft, design the shaft. One, we're going to determine the internal torque, or the internal loading. It's really just like what we've been doing in the past, determine internal loading. And so for at least with power problems, that's going to be associated with this T over P omega. Okay. Yeah. And anyway, like that. Or probably we'll cut and look at a free body diagram and determine internal loads, draw an internal torque diagram, and then calculate stresses. Once we have that internal torque, if we want to design, we're just going to apply the BDR, and that BDR is this tau applied less than or equal to tau allowed for the shaft that I'm designing. Right? When is it going to break? And here, because we have torsion, the relationship for this applied shear stress will be T times the outer radius or radius of the shaft times J, which will be the polar moment divided by J, less than or equal to tau allowed. Okay? And so sometimes, if I'm looking at the cross section of the shaft, sometimes, like in your textbook, the outer radius is labeled C. C is labeled the outer radius, and they use the variable C because that's where the maximum shear stress is going to occur in the outer radius, and we knew that from our stress distribution. So here, this rho and this J becomes C over pi over, here, you know what, I'm going to leave it as J. I'll leave it as J right here. And these two properties, the C and the J right here, they are the properties, these are the only geometric properties associated with the cross section. And so really what we're trying to do is solve for this, like this J over C, or C over J. So if I rearrange this, like this would be T over tau allow less than or equal to J over C. And this J over C right here, sometimes, depending on where you want to look, like sometimes manufacturers will publish this polar moment of inertia over the outer radius, so you can just choose based on this. And they call this a section modulus. And it has units of length cubed. And that's it. It's just, and this would be the geometric property, right? But we can use this, you don't have to use J over C, the section modulus. You can just use it to get the radius directly, right? All right. So that is the relationship between power and torsion in a nutshell and designing it. Yeah. And so now we just have to do some problems. Alright, welcome to office hours, and let's see, we'll do a dynamics problem in this one. And in this problem, let's see, we got some crazy looking thing given. Let's see here. It looks like, we have a particle or object with a mass of 400 kilograms. And it's pulling up on a pulley system deal with, oh my gosh, okay, so here's what it looks like. And anyway, what we need to do is find, in this problem, it'll become more clear when I control the schematic here, we find the velocity, at t equals 2 seconds. The system looks like this. There's like a table here, there's a schematic. And in the schematic, I have a table for straight edge. Alright, so it's like a corner, and then off that corner there's a pulley, and then over here there's a motor. We'll put a motor right there, and then there's a rope. This goes down like that, yeah? And then there's another little pulley here, and there's a crate at the bottom of this, like this, and that crate is what weighs 500 or 400 kilograms. Yes, alright, and this is a motor. Okay, so there's a motor. And, and there's a force, a graph also that's given. The graph of the force in the motor as a function of time, and it looks like it's a parabola like this, and it has a function here, f, as a function of time, is 625 t squared, and the units output is in newtons. So this force is in newtons, and the time is in seconds. Alright. And at 2 seconds, if I plug in 2, 625 times 4 is 2,500 newtons. Alright, in 2 seconds. Alright, great. So what do I need to do in this problem? Well, the force increases from 0 to 2,500 newtons in 2 seconds. Okay. And I have to determine the velocity of the crate at A. So right when it starts lifting off the ground, I need the velocity, right? And so what I need in this problem is the force at which it starts to lift off the ground. Okay. Which really means a static case. Okay. And then that instant the crate just starts to lift off the ground, that'll be the force in the rope, and then I have to apply that force in a dynamic case. All right, good. So let's start with the static case to see what the force in the rope will be, which I think it'll be pretty obvious. But we'll call it the static case. And I guess I have a couple choices. Oh snap! The motor is here, right? And I could do a free body diagram of. It depends what I want to do the free body diagram of, right? But I want to know what the force is that the motor needs to deliver. And because it's in a pulley system, it's different than the force that's in the weight of the particle itself. So really, again, we're assuming that all the pulleys are massless. So essentially what I have is this, I show them the cable, and then I have this free body diagram. And because the pulley's massless, I can make this cut there. I'm cutting here and here, like this. And there would be a force, I'll call this the force in the rope. I'll call that T. And I would have the weight here, I'll call it W. And which way do you want to say it's positive? Up or down?
I could say, I just because the pulley, we could say down is positive.
Okay, down is actually convenient for us later, but we'll say here this is positive y, and then positive x would be to the right, and then here this, because it's a static case, everything equals 0, right? So by equilibrium, now I'm going to apply my equilibrium. Some of the forces in the vertical positive is downwards. Applicate the static case, so I have negative 2t plus the rate equals 0, and that tells me the force that I need in the rope, the tension force, is W over 2, which would be 400 kilograms times 9.81 meters per second squared divided by 2, and that would be 200 times 9.81, which is, was it
196.2.
1960, 196, for sure. Is it 1,962?
What is 196?
400 times 9.81. I got 1962 newtons.
Oh, okay, there we go.
Oh, okay. So 1962 newtons is the force that I need in the cable, and that looks good. Okay. All right. And what else do I need? I think that's it. 1962 newtons, and okay. I get it. This one. Okay. So this 1962 newtons is actually right here the time in which that occurs. The time in which this occurs. Time at 1962 newtons. Or F equals 1962 newtons. That force that the motor is going to deliver to the rope will be, I just take the relationship here. 1962 newtons is equal to 625 times t squared right here, and that would be t is, the 625 is units of newton per second squared, but it's all good. 1962 divided by 625, and then the square root of that is 1.77 seconds. 1.77 seconds. 1.77 seconds. Okay, so that's the time at which the cable, the crate starts to move. Right here. This will be 1.77 seconds. Right here. This is 1962. Okay. Shoot, now what do we need to do? We need to find the velocity at 2 seconds. Okay, so at this case, at 1.77 seconds, the velocity is 0. Okay, the velocity is 0 there at that point. All right, and let's see here. What would the velocity of the, can we determine, oh my gosh, I suspect we're going to need a cable length equation, right? And so I'm going to pick a point here to describe the motor M, and then I have the crate A here, okay? And I have to so here, I'll call this number 3, I'll get a cable length equation. 1, 2, 3, cable length equation. And in this, because we have a pull problem, I need to choose a fixed location. So here, I'll choose a motor as a fixed location to M. I'll call that plus SM, that distance. And then from the pulley here to the cable at A, I'll just say this is part of the cable at A, because that, so I'll call this plus SA. And that would tell me, let's see, interesting, the length of my cable. The one thing I also need is the length here from fixed point to fixed point. I'll call that L. Okay, and the length of the cable I'm interested in is this orange part. I'll use green or red. It would be this plus this. These would be, that red distance would be the cable length that I'm interested in. And this first portion right here is L minus SA, based on the way I chose my reference. I'm sorry, SM, L minus SM, plus 2SA equals 0. And that would tell me, if I take time derivatives, it would tell me minus VM plus 2VA equals 0. And then it would also tell me, I can also get acceleration. This would be telling me minus AM plus 2AA equals 0. Yeah. And we have those relationships. All right. Wow. Okay. Interesting. Okay. All right. Man, this is interesting. This is very interesting. All right. So now I want to look at the dynamic case. Okay. So of particle A. So 1, 2, 3, 4. 4. Let's call this 4. The dynamic case. So it's going to start moving. Okay. And man, I think I'm going to need this as a function of time, right? Okay. So here in my dynamic case, again, I'm drawing the same free body diagram as I did earlier. This thing right here. I'm going to draw this, and then, but it's not going to be equal to 0. So here, I'm going to have here's the particle, here's the rope, here's the pulley, here's the cut face, boom, and this is the tension force T. I think we already established that T equals F, right? We pretty much established that. But this is T, and I would have a weight W, and thankfully, because it was important. If we go back here, it was important that we chose positive SAs downwards, because we want to be consistent with the direction of positive motion in our static or in our force, in our equation of motion. So here, this will be plus Y is positive downwards again. And this time, this does not equal 0. This is one motion. Here's the pulley, here's the mass, and I will have an inertial term, at least in the vertical direction, and I will call that MA. It would be MAY, but this is particle A. It's only moving in one direction, so I can call it MAA, okay, because there's no horizontal motion here. And and so the equilibrium or the equation of motion that's relevant for me here, the E of M, will be sum of the forces downward, right here, is equal to 0, and I'm going to apply F equals ma. And again, that's just going to be negative 2t plus w equals MAA, like this. Okay. And what I have is that t is equal to f, and it's a function. And so here, this would be negative 2 times, what was it, 625 t squared? Negative 2 times 625 newtons per second squared. I'm going to put the units there. Newtons per second squared times t squared plus the weight of the plate plus, not plus, is equal to, plus, here, in fact, forget the weight of the plate, I'll move it like that, is mg, the mass times gravity, is equal to mass times the acceleration of a. Yeah. And what this tells me is that the acceleration of a is negative 2 over m, the mass, 625 newtons per second squared, times t squared, plus g. Yeah? And that means I have acceleration as a function of time. I've created an equation for acceleration of function of time, so that's using numbers. You know, if I...
Wait, shouldn't the parentheses, or I guess never mind, I guess you don't necessarily have to.
Oh, no. Yeah, so here, acceleration of a as a function of time is going to be, let's see, let me make sure the units work out, negative 2 over m, and mass was 400 kilograms?
Yes.
So here, 400 kilograms times 625 kilogram meters per second squared divided by second squared times time squared plus 9.81 meters per second squared. And the kilogram units cancel here. That's convenient. And what I'm left with is that this function is AA is equal to, let me do some calculation, 1250 divided by 400. It would be negative 3.125 meters per second to the fourth times t squared plus 9.81 meters per second squared. Yes. Okay. That's pretty good, right? Okay. And so that means I have the acceleration as a function of time for the particle at A. Right? Okay. And I also know from now I have 1D motion, so now I can look at the kinematic case. 5, kinematics, and this is 1D motion. Particle A is just moving 1D motion here. Okay. And I guess technically speaking, I have the acceleration of the motor as well, right? So I have lots of choices. I could do my 1D motion with A, or I can solve for AM as a function of time and do my 1D motion on M. Is that, yeah? Yeah. So I don't know which way do you do better. You want to do the 1D motion on M or on A?
I was just on A.
On A, so we want to find the velocity. Oh, yes, we'll do it on A because we want the velocity.
We want the velocity there.
Oh, okay, so we might not even move the cable length equation. That's convenient. So here, let's do the 1D motion on A. So on A, so here I know the acceleration of A is a function of time, so AA, and I know that the acceleration is related to dv dt, like this. And so then I just set that equal to, this negative 3.125 meters per second squared, to the fourth, times t squared plus 9.81 meters per second squared. I'm going to set up the integral, which will be, I shouldn't want to waste time there, but it's all good. The integral will be, here, we'll have to write this again one more time, 3.5 meters per second to the fourth times t squared plus 9.81 meters per second squared. dt equals dv.
Wait, where did you get this number?
Which one? That negative 3.15, I multiplied 2 times 625 divided by 400.
Okay. Yeah, I did 5.6.
Oh, okay, no problem. Okay, and now, to get the actual velocity at 2 seconds, let's see, at time t equals, so this was important for me because at time t equals 1.77 seconds is when I start moving. 1.77 seconds is my lower bound of this integral, and in that case, my velocity is 0, right? And then I want to find the velocity at 2 seconds, right there. I can find the velocity as a function of time, too, but in this case, I can go directly to the answer, so velocity at 2 seconds, and so now I integrate and solve with these bounds, and so this would be negative 3.125 meters to the fourth over 3 t cubed plus 9.81 meters per second squared times t, all evaluated from 1.77 seconds to 2 seconds equals v. It's 0 technically, but that's all good. I need that. So v at 2 seconds. At t equals 2 seconds. And that will be, some numbers. Let's see.
I got negative 0.301.
Oh, crap.
Which is right. No.
That doesn't seem. Well, negative actually could. Well, no.
The negative in this case, well, no, it doesn't.
Oh, yeah, negative. Yeah. Oh, yeah. That's right. Because it's moving up. Yes, and so that would be like we said, positive is moving down, so it's moving up. Yeah, so that actually negative would make sense. And in this case, here, let's see, I'll double check too. 1.59?